Good day, everyone. It is nice over here for you and I because learning never ends and education is the key to an impactful life. My name is Anthony Nathaniel. Good day, everyone. I welcome you to the 12th episode of Physics for SS2. And in this particular episode, we are going to be dealing with the reflection of light waves. So I implore you to watch this video to the end to gain as much as possible. About the types of beams. Now, in light rays, the direction of paths along which light energy flows. So such rays are indicated in diagrams by thin lines with arrowheads, which indicate the direction of travel of the light. But then, a collection of rays is called a beam. And there are three types of beam. A parallel beam is one in which the light rays are parallel to one another. So that's the first one you can see here. It consists of different light rays together. A bunch of light rays is called a light beam. Now when you bunch them together and they are traveling in the same direction, it's called a parallel beam. Then next, we also have a convergent beam. A convergent beam is one in which the rays converge to meet at a point. So in this case, in the second diagram, you can see the different rays, they are joining together to meet at a particular point. Then next, we have a divergent beam. Divergent beam is kind of beam that they all come from one point and they spread out or diverge from the point. So lamps produce a divergent beams and torchlights. So these are the three beams of light. When light travels, when these beams from one point to another, they travel in a straight line, and this can be shown by using two cardboard pipes, one straight and the other bent. If we place a candle flame at one end of each pipe and view through the other end, light from the candle flame will be seen clearly on one end of the straight pipe, but no light will be seen at the other end of the bent pipe. So the reason for this is that light travels only in a straight line, so light doesn't bend, it only gets reflected. So this phenomenon of light traveling in a straight line is called a rectilinear propagation of light. And because of this, light can be reversible along the direction in which it travels. So we apply this feature in when we are talking about forming the ray diagrams of concave and convex mirrors, which we'll be talking about later in this episode. The fact that the light rays move in a straight line is enough evidence for us to understand how an eclipse works. Now, an eclipse is basically a position whereby one or more planetary bodies are blocked by another body. Now, for example, you can see this in this case, we have the eclipse of the moon, where the earth is positioned between the sun and the moon, and the moon cannot be visibly seen completely. So in this case, you have a different position. You can have total eclipse when the earth is totally covering the moon, or you could have partial eclipse when the moon is towards the edge of the earth, and then you can have no eclipse when the rays of the sun can still reach the earth, reach the moon. So the reason for this is partly because of the rectilinear propagation of light. So that is one of the real life phenomena that we can understand. Another device that works based on the rectilinear propagation of light, or based on the fact that light traveling in a straight line, is the pinhole camera. So in this case, it's make use of this fact. It has a small hole made with a pin or a needle point. So the opposite end has a screen made of tracing paper on ground glass. Light from an object in front of the pinhole passes through it and forms an image on the screen. If the screen is replaced with a photographic paper or film, a picture of the object can be taken with the pinhole camera. So this is basically how a pinhole camera works. It receives light from the object, and then the inverted image is formed on the film or photographic film. So this is how it works. And basically the pinhole has to be very, very tiny, because if the pinhole if the hole is not sharp, then the image will be bright, but at the end of the day it will be blurry, because a big pinhole is just like a group of smaller pinhole. That means the images will overlap with each other, and at the end of the day you have a blurred image. So it's better to have a very, very tiny pinhole where only one image will be formed, even though it might not be bright. So then you can now, at the end of the day, you can now use digital video editing tools to lighten and edit the video. So that is basically why we have pinholes that are tiny in the camera. So basically, if the distance between the pinhole and the screen is increased, the image will be enlarged, but it will be less bright. But the decrease in brightness is as a result of the distribution of the same amount of light over the greater area of the enlarged image. So basically, this is how a pinhole camera works. Now let's talk about calculating the Magnification. So magnification in terms of light is defined as the ratio of the size or height of the image to the size or height of the original object. Now consider the ray diagram of definition of an image by pinhole camera. So this is a pinhole camera, and here we have that the magnification is equal to the size of the image divided by the size of the object. So basically the size of the image is B complement A complement divided by the size of the object, which is BA. So that is what magnification is. It is basically defined as the size of the image to the size of the object, or the height of the image to the height of the object, or the length of the image to the length of the object. So basically, any ratio of a part of the image to the corresponding part of the object that can be taken can represent the magnification. Now, this is a question which will help us to understand this concept, and the question goes thus: the height of an object placed at a distance of 60 cm from the hole of a pinhole camera is 15 cm. If the length of the camera is 10 cm, calculate the magnification produced by the camera and the height of the image. Now in this case, we are given that magnification is equal to the length of camera divided by the distance of the object from pinhole. That's 10 over 60, that's 0.166. Also, the magnification is equal to the height of image divided by the height of object. So you just equate that to the magnification. That's 1 over 6 equals to height of image over 15, which is the height of the object. Then when we evaluate that, when we make H complement the subject, we'll have 15 over 6, that's 2.5 centimeters, which will be the height, which will be the height of the image. When light hits a plane surface, it is reflected away from that surface, and the way it is reflected depends on the nature of that surface. For example, in this case, when we have an irregular surface, the light reflected is reflected in random directions, and this is called irregular reflection. It is called diffuse reflection too, because the parallel ray of light incident leads to a rough surface are diffused in all directions. The second type of reflection is called irregular reflection, and it's the kind of reflection that occurs when you look at yourself in a mirror. You see a regular reflection. That is why the mirror reflects a regular shape that resembles you. And even if it was a rough surface, it would not be a regular reflection. Instead, it will be like what you see when you look at a rough wall. So you can't see a reflection of you in a rough wall. So that is the mirror works on the principle of a regular reflection. There are two laws of reflection which govern every reflection that you come across in physics. The first law is the incident ray and the reflected ray and the normal at the point of incidence all lie in the same plane. So that means they are on the same straight line and at the same point. That's where they intersect. Now the second law is that this angle of incidence is equal to the angle of reflection. In reflection of light rays, we have two different types of images that are formed when light is reflected. When light is reflected, we can have a virtual image, which is one that cannot be caught on a screen, and which rays of light do not actually pass through, but which is nevertheless visible to the eye. Or we could also have a real image, which is one that can be caught on the screen. Light rays actually pass through a real image. Now, when we talk about the reflection of light can occur on a plane mirror. Now, a plane mirror is a kind of mirror that you often use to look at your reflection. And that plane mirror, there are different properties of the images that are formed when you look at a plane mirror. Now, these are the 5 properties of characteristics of images formed by a plane mirror. The first is that they are the same size as the object. The second is that they are virtual, and number 3, they are laterally inverted. So that means the left side of the shape is projected to the right, and the right is projected to the left. That's called lateral inversion from the side. Then we also have it is as far behind the mirror as the object is in front of it. Then at the end of the day, it is also upright. So these are the 5 major properties of an image that is formed by a plane mirror. Let's talk about instruments that are operated based on the reflection property of light, and that is the periscope. The periscope is a practical application of reflection of light by a plane mirror. It is an instrument used for looking over barriers or obstacles, and in particular, they are used in armor tanks by soldiers to see out above the armor plating. So as you can see in this diagram, we have a periscope. So the light comes from the left to the right, and then it hits one of the mirror, at one of the mirror that's at 45 degrees to the vertical, and then this light is now reflected at vertically downwards to the second mirror. Then the second mirror also reflects the light, and then the reflected ray is now horizontal, and which can now be seen from the eye. So a simple periscope consists of two parallel plane mirrors fixed at one another and inclined at 45 degrees to the walls. So basically, by the reflection of the two plane mirrors, an object hidden from view can be seen by an observer. But the disadvantage of the periscope is that it often produces multiple images. So there are improvements on the periscope, advanced improvements that can also correct this error. There's another phenomenon that we have to explain, which is the effect of mirror rotation on a reflected ray, and this is called a mirror galvanometer in its application. Let's talk about this in this section of this video. Now you can see this is a diagram of a mirror AB. Now when this mirror AB is rotated to mirror CD through an angle theta, the incidence angle is also rotated through an angle theta, and the normal now becomes a new normal. So this adjusted, and the new reflected ray is now NR2. That is the normal, but the normal does not remain the same. The normal has been adjusted to another normal, so that becomes the second normal, and then the new angle of incidence is ONP2. That's from the O to N to P2, where P2 is the new angle of normal. It is a new normal line, which is equal to I plus theta. Note that the normal P1N is also rotated through theta to P2N. So by the law of reflection, the angle of reflection in this new position is also equals to I plus theta. Then the angle P2NR2 is I plus theta. So that's what we get. The angle P2NR2 is also I plus theta. So at the end of the day, the angle between the incidence ray and the new reflected ray equals angle ONR2, which is equal to I theta plus I theta. That's 2I plus theta. So the angle of rotation of the reflected ray when the mirror is turned through theta is 2I plus 2 theta minus 2I. That's 2 theta. That means the reflected ray is rotated by 2 theta. So that means if the incidence ray has a constant direction and the mirror is rotated through an angle of theta, then the reflected ray will be also rotated through an angle of 2. In our study of reflection, we'll be dealing with two types of mirrors, and these mirrors, they are called mirrors. They are different from plane mirrors because they reflect light incident of them, and they are made from the part of surface of spheres. So they are called spherical mirrors, and they have a large number of scientific and practical applications. Shaving mirrors, cadavering mirrors, parabolic mirrors of telescope, mirror reflections of satellites are some examples of applications of spherical mirrors. And there are two types of called mirrors. They are convex and concave mirrors. They are made by silvering a glass surface, which is part of a sphere. If the inside surface is silvered and the outside surface is the reflecting part, then the resulting mirror is called a convex or diverging mirror. However, if the outside mirror is silvered, if the outside surface is silvered and the inside surface is the reflecting part, then the resulting mirror is known as a concave or converging mirror. Like I can see, this is in the first we have a concave mirror, and then finally we have a convex mirror. Now let's talk about the different parts of a mirror. Now you can see here we still have a concave mirror and a convex mirror, but there are essential parts of spherical mirrors, which include the aperture, the pole, the center of curvature, the principal axis, and the radius of curvature. The aperture is the width of the mirror, that is from the top of the mirror to the bottom. Then we have the pole of the mirror is the center of the reflecting surface of the curved mirror. So as you can see, this is the pole. You can see the poles of the two different mirrors, the concave and convex mirrors. They are labeled P. And next we have the radius of curvature, which is distance Cp. It is the radius of the sphere of which the mirror forms a part. Now the radius of curvature, that is the distance from C to P. You can see it from C to P. It's called Cp. Then we have the principal axis is the line PC, from the pole to the center of curvature. So that's, you can also see that the radius of curvature is lying along the principal axis. Then finally we have the way these mirrors operate. First, for a concave mirror, when the parallel rays of light close to and parallel to the principal axis are incident on a concave mirror, they converge or come together after reflection. But on a convex mirror, when such rays are incident on a convex mirror, they diverge from the surface and appear to come from a point F on the principal axis behind the mirror. That is why most of the time we talk about the fact that convex mirror forms virtual images, because these images appear to diverge from that principal focus. One very important point on a mirror is known as the principal focus. And this principal focus of a curved mirror is the point on the principal axis to which incident rays parallel and close to the principal axis converge, or from which they appear to diverge after reflection. Now, the principal focus is by experiment and by the geometry of this is found to be equal to half of the radius of curvature for both concave and convex mirror. That means F equals R over 2. Thus, the principal focus is midway between the pole and the center of curvature in a mirror.
The size, nature, and position of the image formed by curved mirrors often depends on the position of the object from the pole of the mirror. So we can investigate this by setting up a setup like this, making use of a concave mirror. You can use an illuminated object, a concave mirror, and a screen. Now, when you put the concave mirror on the stand, and the light is made to fall on the object by the adjustment of the light, the mirror, you slightly turn it to one side so that the image will be formed sharply when possible. Now, you will notice that when the distance of the screen is adjusted, you will see that the image is found to be diminished, real, and inverted. If you place the object very far from the mirror, it will be diminished, real, and inverted. Then if the object is moved closer, the image becomes larger but will still be inverted, and so on and so forth. So there are different ways of getting these positions, and we have a very easy graphical way of representing this pair of image and object positions, and it is known as ray diagrams. These are the ray diagrams for a concave mirror. Now, for this concave mirror, you can see in the first diagram, you can see that when the object is beyond C, that is from OX, when the object is beyond C, when we combine the ray diagrams, we have our image which is between F and C, and it's also real, inverted, and diminished. Then secondly, when our object is at C, then the image is also at C and it's real, inverted, and is the same size as the object. Then thirdly, when the object is between and C, then the image is beyond C, real, inverted, and magnified. Then finally, when the object is at the focus, which is F, then the image is at infinity, is also real, inverted, and magnified. So just in case you don't know, these labels are: P stands for the pole, which is the center of the reflecting surface of the mirror. Then F stands for the focus, which is half of the radius of curvature of the mirror. Then your C stands for the center of curvature, that is the radius of the sphere from which the mirror was produced. Finally, for a concave mirror, we also have a position where the object is between the pole of the mirror and the focus. So in this case, if the object is between the pole of the mirror and the focus, that means when you trace the ray diagram from the top of the object, which is parallel, which will pass through the focus, then you trace another one to pass through the center, and then you trace them forward behind the mirror. That is the polished surface. So behind the mirror, you have them joined together, and when they join together, they will form a virtual image. So the reason why this is virtual is because it is formed on the opposite side of the mirror, and it is formed behind the mirror. So that's why it's a virtual image. And this virtual image, it is gotten when you have your object between your focus and the pole of the mirror. So in this case, this kind of image is behind the mirror. It's virtual, it is erect, and it is magnified. In the case of a convex mirror, the image is formed by a convex mirror irrespective of the position of the object are always virtual. So, and they are always diminished. So a convex mirror forms only virtual, erect, and diminished images. So the image formed is at the intersection of the reflected or reflected rays produced backwards in broken lines, and it is formed behind the mirror. This is the case for all positions of the object in front of the mirror. So you can see this when you have an object in front of the mirror, when you project it in parallel line. So a parallel line will meet the focus, will be reflected to the focus. Then a line passing through the center of the mirror will be reflected undeviated. So at the end of the day, we'll have the lines intersect at behind the mirror, and then you have a diminished image. So that is how it is. They are always smaller than the object. Now let's talk about one experimental way of determining the focal length of a mirror. That is by using the mirror equation. Now the object distance u, the image distance v, and the focal length of spherical mirrors are related by the equation 1 over u plus 1 over v equals 1 over f. So this is called the mirror equation, and you can always derive it by using this experimental procedure. So the equation can be used to obtain the focal length, and experimentally you can describe it. You can use an experimental method to look for the focal length by setting up an illuminated object like the crosswire of a ray box, and it is placed at a distance of about 3 over 2 of the focus in front of the mirror. Then the exact distance is measured. So basically you just measure the object distance, measure the image distance when you get a sharp image from that object. Then you plot the graph of the inverse of u against the inverse of v. So by that, when you get the slope, when you calculate the slope of that graph, it will have the reciprocal of the intercept at each axis will give the value of the focal length. So basically that's one way of determining the focal length of a spherical mirror. Finally, there are different uses of mirrors or spherical mirrors. You can use curved mirrors or spherical mirrors. You can use them as shielding mirrors, because when you place your face in front of the mirror and close to it, you can see an enlarged, erect, and virtual image of your face. That is one use of spherical mirrors. Now, that's not all. You can also use concave mirrors as reflectors in reflecting telescope and microscopes. You can use convex mirrors as driving mirrors in motor cars, because you give an erect image of the object behind the driver. In addition, you can use convex mirrors to produce a wide field of view, because they are very useful in diverging light, so they make everything wider. So objects within a large angle can be seen with the help of convex mirrors. So these are all the uses of mirrors, and then you can also use parabolic mirrors as in car headlamps and searchlights. So it's a special type of mirror which has it's a special type of concave mirror which has the shape of a parabola, and the parabolic mirror produces a wide parallel beam of light of constant intensity when a small light source is placed as its focus. So basically, the reverse is also true. So anytime you have a parallel beam of light coming to the parabolic mirror, it converges as its focus. So those are the uses of mirrors. We've come to the end of this video, and before we go, there's a question on the screen which you can try out, and you can also forward the answers to the WhatsApp number in the description of this video. Thank you for watching, and see you next episode.